Example, if a study is looking at the effects of a new exercise program on weight loss, a confounding variable could be diet, since changes in diet can also affect weight loss. 2. Impact on research. Confounding variables can lead to incorrect conclusions. Researchers may mistakenly attribute effects to the independent variable when, in reality, the confounding variable is influencing the outcome. Example, if the exercise program coincides with participants also changing their diet to healthier options, it becomes difficult to determine if weight loss is due to the exercise or the diet. What are extraneous variables? Extraneous variables are any variables other than the independent variable that can affect the dependent variable. While they're not necessarily confounding variables, they can still introduce noise into the study and potentially weaken the conclusions. Key concepts. 1. Definition. An extraneous variable is a variable that the researcher did not control or account for, but it may still have an effect on the dependent variable. Example, in an experiment measuring the effect of studying environments on test scores, lighting in the study area could be an extraneous variable. Poor lighting could affect concentration and performance, even if the study environment is otherwise consistent. 2. Difference from confounding variables. While confounding variables are specifically linked to altering the perceived relationship between the 4 and dV, extraneous variables may not directly interfere with that relationship, but can still impact the dV. Example, using the example of the study environment again, if students are tested at different times of day, fatigue or alertness could affect test scores. This doesn't directly confound the study, but may introduce variability in scores due to those extraneous factors. Important details. 1. Control measures. To reduce the impact of confounding and extraneous variables, researchers take steps during the design and implementation of a study. Randomization. Participants are randomly assigned to different groups to help balance out confounding variables. Control groups. Using control groups helps to account for extraneous variables by comparing outcomes against a group that does not receive the treatment or intervention. Standardization. Ensuring that extraneous variables are kept consistent for all participants can minimize their impact. 2. Evaluating studies. When reviewing research, it's important to consider whether confounding and extraneous variables have been adequately controlled for, as this affects the validity of the findings. Researchers should report potential confounding variables and explain how they were addressed. Examples. Example 1. Impact of sleep on academic performance. 1. Independent variable, amount of sleep. 2. Dependent variable, academic performance. 3. Confounding variable, study habits. If students who sleep more also have better study habits, it becomes difficult to determine if sleep alone is causing better performance. 4. Extraneous variable, stress levels. A student's stress may vary independently of sleep, affecting their test performance and potentially introducing variability into the results. Example 2. Effect of a new teaching method. 1. 4. The teaching method used. 2. DV, student test scores. 3. Confounding variable, prior knowledge. If one group has students with significantly higher prior knowledge than the other, it could impact test scores regardless of the teaching method. 4. Extraneous variable, classroom environment. Factors like distractions in the classroom, temperature, or seating arrangements can affect student attention and, consequently, test performance. Conclusion. Confounding variables and extraneous variables are crucial concepts in research design. Confounding variables can distort the relationship between independent and dependent variables, leading to misleading conclusions. Extraneous variables can introduce noise or variability, but may not directly confound the results. To conduct valid and reliable research, it is essential to identify and control for these variables as much as possible. Understanding these concepts will be beneficial as you prepare for your CPC exam and critically evaluate research findings. Covariables. Sure, let's dive into the concept of covariables in the context of ANCOVA. This is an important statistical method used in research, especially when comparing groups while controlling for other variables. We'll break down the key concepts, important details, and provide examples to help clarify everything. What are covariables? Covariables are variables that are not the main focus of a study, but may influence the dependent variable. In ANCOVA, these covariables are included in the analysis to control for their effects, helping researchers get a clearer picture of the relationship between the independent variable and the dependent variable. Key concepts. 1. Purpose of covariables. Covariables are included in statistical analyses to control for variability that could skew the results. By accounting for these variables, researchers can make more accurate comparisons between groups. Example: in a study examining the effect of a new teaching method on student performance, prior knowledge of the subject matter might be a covariable. Controlling for prior knowledge would help isolate the effect of the teaching method on performance. 2. Independent variable and dependent variable. The independent variable is what you manipulate in an experiment. The dependent variable is what you measure. Covariables help explain variations in the dependent variable that are not due to the independent variable. 3. ANCOVA overview. ANCOVA combines ANOVA and regression analysis. It allows researchers to compare two or more groups while controlling for one or more covariables. The goal is to evaluate whether the mean differences among groups on the dependent variable are still significant after accounting for the covariables. Important details. 1. Selecting covariables. Researchers choose covariables based on prior research, theoretical reasoning, or exploratory analysis. It's important to select covariables that are likely to affect the dependent variable. Example: if studying the effect of exercise on stress reduction, relevant covariables might include baseline stress levels, age, and physical health status. 2. Statistical adjustment. ANCOVA adjusts the means of the dependent variable for the covariables. This means it statistically controls for those variables so that their influence is removed from the analysis. This helps provide a clearer comparison of the effects of the independent variable on the dependent variable. 3. Interpretation of results. In ANCOVA, if the 4 remains significant after accounting for the covariables, it suggests that the independent variable has a genuine effect on the dependent variable. If the significance disappears, it may imply that the covariables are influencing the relationship. Example of covariables in ANCOVA. Let's imagine researchers want to study the effect of 2 different exercise programs on weight loss. 1. Research goal: to compare the effectiveness of Program A and Program B on weight loss over 8 weeks. 2. Independent variable: the type of exercise program. 3. Dependent variable: the amount of weight lost by participants. 4. Covariables. Age: older individuals might lose weight differently compared to younger ones. Baseline weight: participant starting weight could affect how much weight they lose over time. Diet: as mentioned previously, participants' eating habits might influence their weight loss. 5. Conducting ANCOVA. Researchers collect data on weight loss after the 8-week period and include age, baseline weight, and diet as covariables in their analysis. By using ANCOVA, researchers can control for these covariables to see if there is a significant difference in weight loss between the 2 exercise programs. 6. Interpreting results. If ANCOVA shows that, after controlling for age, baseline weight, and diet, Program A leads to significantly more weight loss compared to Program B, researchers can conclude the exercise program type has an effect on weight loss, independent of those covariables. Conclusion. Covariables are important elements in ANCOVA that help researchers control for additional factors affecting the dependent variable. By including and analyzing these variables, researchers can make more accurate comparisons between groups and draw clearer conclusions about the effects of the independent variable. Understanding covariables in the context of ANCOVA will help you critically evaluate research findings as you prepare for your CPC exam. Hypotheses. Experimental or alternative hypothesis. Sure, let's break down the concepts of the experimental hypothesis. This is a key concept in research and statistics that helps researchers formulate their studies and make predictions about outcomes. We will cover its key concepts, important details, and examples to help clarify everything. What is an experimental hypothesis? The experimental hypothesis is a statement that suggests a specific effect or difference will occur in a study. It proposes that there is a relationship between the independent variable and the dependent variable, meaning that manipulating the 4 will lead to changes in the DV. Essentially, it is the researcher's prediction about what they expect to find. Key concepts. 1. Formulation. The experimental hypothesis is created before conducting the study and is tested through the research. It often posits that there will be a significant difference or effect due to the independent variable. Example. In a study examining whether a new teaching method improves test scores, the experimental hypothesis might state, students who use the new teaching method will score higher on the test than students who use the traditional method. 2. Notation. The alternative hypothesis is typically denoted as H or H. It is often contrasted with a null hypothesis, which states that there is no effect or no difference between groups in the population. The null hypothesis represents a default position that indicates no relationship or effect exists. 3. Types of hypotheses. There are 2 main types of hypotheses. Directional hypothesis. This type predicts the direction of the expected effect. For example, students who study more will achieve higher test scores. Non-directional hypothesis. This type predicts only that there will be a difference but does not specify the direction. For example, there will be a difference in test scores between students who study more and those who study less. Important details. 1. Testing the hypothesis. Researchers design experiments to test the experimental hypothesis. They collect data and analyze the results to see if the evidence supports the hypothesis. If the results show a significant difference, researchers reject the null hypothesis and support the alternative hypothesis. Example. If the data shows that students using the new teaching method score significantly higher than those using the traditional method, the researchers would conclude that the experimental hypothesis is supported. 2. Importance. The experimental hypothesis directs the researcher's focus and helps determine the study's design, data collection methods, and analysis. Clearly defining the experimental hypothesis is crucial, as it establishes what the researchers aim to investigate. 3. Statistical significance. Researchers often use statistical tests to determine whether the results are statistically significant. This means that the observed effect or difference is unlikely to have occurred by chance. A common level of significance used in research is p less than 0.5, meaning there is less than a 5% probability that the observed results are due to random chance. Example of an experimental hypothesis. Let's say researchers want to investigate the effect of sleep on test performance among high school students. 1. Research question. Does the amount of sleep affect students' test scores? 2. Independent variable. Amount of sleep. 3. Dependent variable. Test scores. 4. Experimental hypothesis. High school students who get more than 8 hours of sleep will perform better on tests than those who get less than 6 hours of sleep. 5. Null hypothesis. There is no difference in test scores between students who get more than 8 hours of sleep and those who get less than 6 hours of sleep. 6. Conducting the study. Researchers conduct an experiment, collect test scores from both groups, and analyze the data to see if there is a significant difference. 7. Interpreting results. If the results show that the high sleep group has significantly higher test scores, the researchers support the experimental hypothesis and may reject the null hypothesis. Conclusion. The experimental hypothesis is an essential part of research design that predicts a specific effect or difference related to the independent variable and the dependent variable. By clearly stating this hypothesis, researchers can focus their studies and look for significant evidence to support their claims. Understanding experimental hypotheses will help you evaluate research findings as you prepare for your CPC exam. Null hypothesis. Sure, let's dive into the concept of the null hypothesis. This is an important idea in research and statistics that helps researchers understand whether their findings are significant or not. We will break down its key concepts, important details, and provide examples to make everything clear. What is the null hypothesis? The null hypothesis is a statement that suggests there is no significant difference, effect, or relationship between variables in a study. It serves as the default position that the researcher tries to test against. Essentially, it's the hypothesis that proposes that any observed differences are due to chance rather than a specific cause. Key concepts. 1. Purpose of the null hypothesis. The null hypothesis provides a foundation for statistical testing. It allows researchers to determine whether their observations are significant enough to reject this hypothesis. Researchers often aim to show that their experimental hypothesis is true by rejecting the null hypothesis. 2. Statement of no effect. The null hypothesis typically states that there is no effect, no difference, or no association between the independent variable and the dependent variable. Example: in a study examining the effect of a new drug on blood pressure, the null hypothesis might state, there is no difference in blood pressure between patients taking the drug and those taking a placebo. 3. Statistical testing. Researchers conduct statistical tests to evaluate the null hypothesis. They collect data and analyze it to see if the results are statistically significant, meaning that they are unlikely to have occurred by chance. A common significance level used is p less than 0.5, indicating a less than 5% probability that the observed results are due to random chance. Important details. 1. Decision-making. After analyzing the data, researchers have two main options. Reject the null hypothesis. If the data show a statistically significant result, researchers will conclude that there is enough evidence to support the alternative hypothesis. Fail to reject the null hypothesis. If the data do not show a statistically significant result, researchers do not have enough evidence to support the alternative hypothesis, and they will retain the null hypothesis. It's important to note that failing to reject the null hypothesis does not prove that it is true. It simply means there isn't enough evidence to suggest otherwise. 2. Examples of null hypotheses. Education. There is no difference in test scores between students taught with method A and those taught with method B. Health. The new diet has no effect on weight loss compared to the standard diet. Psychology. There is no relationship between stress levels and academic performance among college students. 3. Null hypothesis in research design. The null hypothesis is a vital part of research design because it helps clarify the focus of the study and what researchers are trying to prove or disprove. It sets the stage for how the study will be conducted and what data will be collected. Example of a null hypothesis in a study. Let's consider a study examining whether a specific study technique improves student performance on exams. 1. Research question: does the use of flashcards improve exam scores among high school students? 2. Independent variable: the use of flashcards for studying. 3. Dependent variable: exam scores. 4. Null hypothesis: there is no difference in exam scores between students who use flashcards and those who do not use flashcards. 5. Experimental hypothesis: students who use flashcards will score higher on exams than those who do not use flashcards. 6. Conducting the study. Researchers conduct an experiment where two groups of students study for the same exam, with one group using flashcards and the other not. 7. Analyzing data. After the exam, researchers analyze the scores to see if there is a significant difference between the two groups. 8. Interpreting results. If the results show that students using flashcards scored significantly higher on the exam, the researchers may reject the null hypothesis and support the experimental hypothesis. If there is no significant difference in the scores, the researchers will fail to reject the null hypothesis, concluding that flashcards do not have a measurable effect on exam scores. Conclusion. The null hypothesis is a fundamental concept in research that proposes there is no significant difference or effect between variables. It serves as the baseline statement that researchers test against when analyzing their data. Understanding the null hypothesis is essential for critically evaluating research findings and determining the significance of results, which is key as you prepare for your CPC exam. Hypothesis testing. Sure, let's explore the concept of hypothesis testing, particularly in the context of the work of statistician R.A. Fisher. This is a fundamental topic in statistics and research methodology, and it's crucial for understanding how scientists and researchers draw conclusions from their data. We'll break down the key concepts, important details, and provide examples to help clarify everything. What is hypothesis testing? Hypothesis testing is a statistical method used to examine a claim or hypothesis about a population parameter based on sample data. The goal of hypothesis testing is to determine whether there is enough evidence in the sample data to support or reject a specific hypothesis. Key concepts. 1. Hypotheses. In hypothesis testing, we typically deal with two types of hypotheses. 1. Null hypothesis. This is the hypothesis that states there is no effect or no difference. It serves as a starting point for the analysis. Example: there is no difference in test scores between students who study with flashcards and those who do not. 2. Alternative hypothesis. This is the hypothesis that states there is an effect or a difference. It represents what the researcher aims to prove. Example: students who study with flashcards will score higher on tests than those who do not. 2. Testing procedure. The testing process involves several steps. 1. Formulate hypotheses. Clearly define the null and alternative hypotheses. 2. Choose a significance level. This is the threshold for determining statistical significance, commonly set at 0.05. It represents a 5% risk of rejecting the null hypothesis when it is actually true. 3. Collect data. Gather data through experiments or observations. 4. Select a statistical test. Based on the type of data and hypotheses, choose an appropriate test. 5. Calculate test statistic. Perform the selected statistical test and calculate the test statistic. 6. Make a decision. Compare the test statistic to a critical value or use a p-value to determine whether to reject or fail to reject the null hypothesis. 3. P-value. The p-value is the probability of obtaining results at least as extreme as the observed results, assuming the null hypothesis is true. A small p-value indicates strong evidence against the null hypothesis, leading to its rejection. Example: if you obtain a p-value of 0.03, it suggests that there is a 3% chance that the observed results would occur under the null hypothesis, which is considered strong evidence to reject H. Important details. 1. R.A. Fisher contributions. Ronald A. Fisher was a pioneer in statistics, notably developing foundational concepts in hypothesis testing, including the use of p-values and significance testing. He introduced the idea of using probability to determine whether hypotheses should be accepted or rejected based on sample data. His work laid the groundwork for modern statistical methods. 2. Type 1 and Type 2 errors. Type 1 error. This error occurs when a null hypothesis is incorrectly rejected when it is actually true. The significance level represents the probability of making this error. Type 2 error. This error happens when the null hypothesis is not rejected when it is false. The probability of making a Type 2 error is denoted by beta. Researchers aim to minimize the risk of both types of errors in their studies. 3. Practical application. Hypothesis testing is used in various fields, including psychology, medicine, business, and social sciences, to make decisions and draw conclusions based on empirical data. It helps researchers evaluate the effectiveness of treatments, compare groups, and assess relationships between variables. Example of hypothesis testing. Let's say researchers want to study whether a new study method improves student grades. 1. Research question: does the new study method lead to higher grades? 2. Null hypothesis. There is no difference in grades between students using the new study method and those using the traditional method. 4. Significance level, set at 0.05. 5. Data collection. Researchers conduct an experiment with two groups. One learns using the new method and the other using the traditional method. 3. Alternative hypothesis. Students using the new study method will have higher grades than those using the traditional method. 6. Statistical test. After the experiment, researchers choose a t-test to compare the average grades between the two groups. 7. Calculate p-value. The statistical analysis yields a p-value of 0.02. 8. Decision. Since the p-value is less than the significance level, the researchers reject the null hypothesis. 9. Conclusion. The researchers conclude that the new study method likely leads to higher grades among students compared to the traditional method. Conclusion. Hypothesis testing is a critical statistical method that allows researchers to analyze data and draw conclusions about hypotheses related to populations. R.A. Fisher's contributions to this field laid the groundwork for understanding how to evaluate hypotheses using statistical evidence. By following a structured process that includes formulating hypotheses, collecting data, and analyzing results, researchers can make informed decisions based on empirical findings, which is essential for your preparation for the CPC exam. Specific study designs. ABABA design. Sure, let's explore the ABABA design, which is a type of experimental design often used in behavioral research, especially in the field of psychology. Understanding this design is important for evaluating how interventions affect behavior over time. We'll break down the key concepts, important details, and examples to help clarify everything. What is ABABA design? The ABABA design is a type of single-subject experimental design. It's used when researchers want to investigate the effect of an intervention on a specific individual or a small group. In this design, A represents the baseline phase and B represents the intervention phase. The alternation between these phases helps assess the effect of the intervention. Key concepts. 1. Phases of ABABA design. The design consists of alternating phases. A phase. This is the initial phase where the researcher observes and measures the behavior without any intervention. This helps establish a baseline for comparison. B phase. This phase involves applying the intervention or treatment to see how it affects the behavior being observed. This pattern repeats to help analyze the effects of the intervention further. 2. Purpose. The main goal of the ABABA design is to show whether changes in behavior are due to the intervention itself rather than other external factors. By comparing behavior across different phases, researchers can determine if the intervention has a positive or negative effect. 3. Visual representation. Researchers often visualize the results of an ABABA design using a graph, where the x-axis represents time and the y-axis represents the measured behavior. Different segments of the graph correspond to the A and B phases. Important details. 1. Advantages. Control. The ABABA design allows researchers to control for other variables and demonstrate a clear cause and effect relationship between the intervention and behavior. Flexibility. It can be adapted for different research questions and is especially useful in studying individual cases. 2. Limitations. Generalizability. Findings from a single subject design may not be easily generalized to a larger population since it focuses on a specific individual or small group. Ethical considerations. Withdrawing an intervention may not always be ethical, especially if the intervention is beneficial. Example of ABABA design. Let's say researchers want to study the effect of a new reading program on a student who struggles with reading. 1. Research question. Does the new reading program improve the student's reading fluency? 2. Baseline phase. In the first A phase, the researcher records the student's reading fluency without any intervention. For instance, the initial observation shows the student reads 50 words per minute. 3. Intervention phase. In the first B phase, the researcher introduces the new reading program for 4 weeks. During this time, they again measure the student's reading fluency. The student's reading fluency increases to 70 words per minute. 4. Second baseline phase. The researcher then withdraws the reading program and continues to monitor the student's progress. After 4 weeks, the reading fluency drops back down to 55 words per minute, indicating a return to baseline performance. 5. Seconde intervention phase. Next, the researcher reintroduces the reading program and measures the student's reading fluency again. This time, the student reaches 75 words per minute. 6. Interpreting results. The repeated measurements show that when the reading program is applied, the student's reading fluency improves. When the program is removed, the fluency decreases, suggesting a clear relationship between the intervention and the behavior. Conclusion. The ABABA design is a powerful single-subject research method that helps evaluate the effects of interventions by alternating between baseline and intervention phases. By observing changes in behavior, researchers can make informed conclusions about the effectiveness of an intervention. This understanding is valuable as you prepare for your CPC exam, especially when considering various research methods and their applications in behavioral studies. Single-subject design. Sure, Let's explore the concept of single-subject design, often referred to as ideographic design. This is an important research method in psychology and behavioral sciences that focuses on studying individual cases in detail. We will break down the key concepts, important details, and provide examples to make everything clear. What is single-subject design? Single-subject design is a research method used to study the behavior, experiences, or outcomes of an individual or a small group, rather than looking at large populations. This approach allows researchers to closely observe changes over time in a specific subject in response to interventions or treatments. Key concepts. 1. Focus on the individual. Single-subject designs center on understanding how an intervention, treatment, or condition affects one person or small number of people. This contrasts with traditional designs that typically look at groups and aim for generalizable results. 2. Repeated measures. In this design, the same subject is measured multiple times over different phases or conditions. This could involve taking measurements before and after an intervention or treatment to see how behavior changes. 3. Phased approach. A common structure in single-subject design includes phases such as baseline phase, the initial observation period where behaviors are recorded without any intervention. This establishes a baseline to compare against. Intervention phase, periods when a specific treatment or intervention is applied to see if it causes a change in behavior. Sometimes this structure can include alternating or withdrawing the intervention to help confirm its effectiveness. Important details. 1. Advantages. Detailed insights. Single-subject designs allow for an in-depth understanding of individual behavior and how it changes over time. Flexibility. Researchers can adapt the design to meet the specific needs of the study, adjusting for different types of interventions and measurement techniques. Ethical considerations. In some cases, it is preferable to study individuals rather than groups, especially when withholding treatment from a group may raise ethical concerns. 2. Limitations. Generalizability. Results from a single-subject design may not be easily generalized to larger populations. Findings may apply to that specific individual, but not to others. Data interpretation. Understanding the impact of other external factors can be challenging. 3. Applications. Single-subject designs are commonly used in clinical settings, educational interventions, and behavioral therapy. They can help evaluate the effectiveness of treatments for conditions such as anxiety, ADHD, or learning disabilities. Example of single-subject design. Let's say a psychologist wants to study the effectiveness of a relaxation technique in reducing anxiety for a single student. 1. Research question. Does the relaxation technique help reduce the anxiety levels of a high school student? 2. Baseline phase. The psychologist first measures the student's anxiety levels using a standardized questionnaire over a 2-week period without any intervention. The baseline average score is recorded. Point intervention phase. After establishing the baseline, the psychologist introduces the relaxation technique for the student to practice daily. During this phase, the psychologist continues to measure the student's anxiety levels weekly. 4. Repeated measures. The psychologist records the anxiety levels at the end of each week of the intervention. If the scores show a decrease, it suggests the relaxation technique may be effective. 5. Withdrawal or alternating phases. To strengthen the findings, the psychologist might temporarily withdraw the relaxation technique and measure anxiety levels again. If the scores increase after the technique is withdrawn, this strengthens the case for the technique's effectiveness. The psychologist might then reintroduce the relaxation technique to see if anxiety decreases again. 6. Interpreting results. If anxiety levels decrease significantly during the intervention and increase upon withdrawal, the psychologist can conclude that the relaxation technique likely had a positive effect on reducing the student's anxiety. Conclusion. Single-subject design is a valuable research method that focuses on in-depth analysis of individual behavior over time. By measuring changes through repeated observations in response to interventions, researchers can gather detailed insights into the effectiveness of treatments while accounting for unique characteristics of individuals. Understanding this design is important as you prepare for your CPC exam because it highlights the importance of personalized approaches in psychological research and practice. Nomothetic design. Absolutely. Let's explore the concept of nomothetic design, which is a research approach that focuses on studying groups rather than individuals. Understanding this design is crucial for analyzing how researchers gather and interpret data to draw conclusions about larger populations. We'll break down the key concepts, important details, and provide examples to help clarify everything. What is nomothetic design? Nomothetic design refers to a research method that seeks to identify general laws or principles by studying groups of people. Instead of focusing on individual cases, nomothetic research aims to make conclusions that can apply to broader populations. This approach is common in fields like psychology, sociology, and medicine. Key concepts. 1. Focus on groups. Nomothetic design studies groups of subjects rather than individuals. Researchers gather data from many people to identify trends, patterns, or relationships among variables. Example: a researcher might study the effects of a new teaching method on student performance by analyzing test scores from an entire class or school rather than just one student. 2. Generalizability. One of the main goals of nomothetic research is to produce findings that can be generalized to a larger population. This means the results can be applied to people outside the specific sample studied. 3. Hypothesis testing. Nomothetic designs typically involve hypothesis testing, where researchers formulate hypotheses about relationships between variables and then collect data to support or refute those hypotheses. For instance, a researcher may hypothesize that increased physical activity leads to improved mental health across a population. Important details. 1. Research methods. Common research methods used in nomothetic designs include surveys and questionnaires, collecting information from a large number of people on their opinions, behaviors, or experiences. Experiments, testing hypotheses by manipulating one variable while controlling others to see its effect on a group. Longitudinal studies, observing the same group of individuals over time to see how variables change. 2. Statistical analysis. Because nomothetic research involves groups, statistical methods are often employed to analyze data. Researchers might use statistical tests to determine if the results are significant and to assess relationships between variables. Statistical significance helps researchers decide whether to accept or reject their hypotheses based on data patterns. 3. Strengths and limitations. Strengths. Nomothetic designs can identify general trends that apply to larger populations, which helps form theories and inform practices. They allow researchers to gather data from a wide range of participants, increasing the validity of the findings. Limitations. Individual differences within groups may be overlooked, leading to conclusions that do not account for unique factors affecting specific individuals. Generalizing results from a sample to the entire population requires careful consideration of the sample's representativeness. Example of nomothetic design. Let's say researchers want to investigate the impact of sleep on academic performance among high school students. 1. Research question: does the amount of sleep affect students' test scores? 2. Hypothesis: high school students who get at least 8 hours of sleep will perform better on tests than those who get less than 6 hours of sleep. 3. Nomothetic approach. Researchers gather a representative sample of students from several high schools to ensure diversity in age, gender, and academic performance. They administer surveys asking about students' sleep habits and track their test scores over a semester. 4. Data analysis. Researchers use statistical methods to analyze the relationship between hours of sleep and test scores across the sample. They might calculate averages and compare performance between students who sleep more and those who sleep less. 5. Interpreting results. If the analysis shows that students who sleep more consistently have higher test scores, the researchers may conclude that increasing sleep can positively impact academic performance. These findings can be generalized to other high school students, supporting the idea that sleep is crucial for learning and academic success. Conclusion. Nomothetic design is a research approach that focuses on studying groups to identify general principles and relationships within a population. By utilizing hypothesis testing and statistical analysis, researchers can make broader conclusions about how variables affect behaviors and outcomes. Understanding this design is important as you prepare for your CPC exam because it emphasizes the importance of evidence-based practices grounded in research findings that apply to larger groups. Factorial design. Sure, let's explore the concept of factorial design, which is a research method that allows researchers to study the effects of two or more independent variables on a dependent variable. This design is commonly used in experimental research and can provide valuable insights into how different factors interact with each other. We'll break down the key concepts, important details, and provide examples to clarify everything. What is factorial design? Factorial design is a type of experimental design that investigates the effects of two or more independent variables and their interactions on a dependent variable. It allows researchers to look at not just the individual impact of each variable, but also how they work together to affect outcomes. Key concepts. 1. Independent variables. These are the factors that researchers manipulate to see how they affect the dependent variable. In a factorial design, there are multiple independent variables. Example, in a study examining study habits, researchers might look at two IVs, the type of study method and the time of day. 2. Dependent variable. This is the outcome that researchers measure to see how it is affected by the independent variables. Example, in the study habits example, the dependent variable could be the student's test scores. 3. Levels of each 4. Each independent variable can have different levels or conditions. For instance, in our example, the study method has 2 levels and the time of day has 2 levels. 4. Interaction effects. One of the key advantages of factorial design is that it allows researchers to study interactions between independent variables. An interaction effect occurs when the effect of one independent variable depends on the level of another independent variable. Example, the effectiveness of flashcards might depend on whether students study in the morning or the evening. Researchers can analyze if using flashcards is more beneficial during one time than the other. Important details. 1. Types of factorial designs. Full factorial design. Every possible combination of levels of the independent variables is tested. For example, with 2 IVs, each with 2 levels, there would be a total of 22 is equal to 42 times 2 equals 422 is equal to 4 combinations or conditions. Fractional factorial design. Instead of testing all combinations, researchers only test a subset of combinations. This is useful when resources are limited. 2. Main effects and interaction effects. Main effect. The effect of one independent variable on the dependent variable while ignoring the other independent variables. Interaction effect. How the effect of one independent variable changes at different levels of another independent variable. Example. In a 2x2 design, researchers can separately analyze the main effects of study methods and time of day and also check for an interaction effect. 3. Data analysis. Researchers often use analysis of variance to analyze data from factorial designs. ANOVA helps determine whether the differences observed in the dependent variable are statistically significant. Example of factorial design. Let's look at a specific example of factorial design to see how it works. Study example. Researchers are examining the effects of a new exercise program on weight loss. 1. Research question. How do different types of exercise and dietary plans affect weight loss? 2. Independent variables. Type of exercise. Level 1. Strength training. Level 2. Cardio dietary plan. Level 1. High protein. Level 2. Low carb. Dependent variable. Amount of weight lost after 8 weeks. 4. Design. This creates a 2x2 factorial design, meaning there are 2 independent variables, each with 2 levels. Thus, the researchers will test 4 combinations. Strength training plus high protein strength training plus low carb cardio plus high protein cardio plus low carb. 5. Data collection. Participants are randomly assigned to one of the 4 groups, and researchers measure the weight loss of each group after the 8-week program. 6. Data analysis. Researchers analyze the data to determine if there are main effects of the type of exercise and dietary plans, as well as any interaction effects. 7. Interpreting results. If the analysis shows that the combination of cardio and a low-carb diet leads to the greatest weight loss compared to the other groups, researchers can conclude that not only do both independent variables affect weight loss, but they also interact in a specific way. Conclusion. Factorial design is a powerful research method used to explore the effects of two or more independent variables on a dependent variable, as well as the interactions between those variables. This design helps researchers understand complex relationships and provide insights that can be applied to real-world situations. Mastering the concept of factorial design will be beneficial as you prepare for your CPC exam, particularly in understanding how different factors can influence outcomes in psychological research. Solomon four-group design. Sure, let's break down the concept of the Solomon four-group design, a research method used in experimental studies to assess the effects of an intervention while controlling for potential biases. Understanding this design is important as it helps researchers make accurate conclusions about their findings. We'll explain the key concepts, important details, and provide examples to clarify everything. What is Solomon four-group design? The Solomon four-group design is a type of experimental design that helps researchers evaluate the effectiveness of an intervention. It combines features of both pre-test, post-test designs and post-test only designs to control for the effects of pre-testing on the outcomes. This design is particularly useful for determining not only the overall effect of an intervention, but also how a pre-test might influence the results. Key concepts. 1. Groups. In the Solomon four-group design, participants are divided into 4 different groups. 1. Group 1. Participants receive a pre-test, undergo the intervention, and then take a post-test. 2. Group 2. Participants receive a pre-test, but do not undergo the intervention. They then take a post-test. 3. Group 3. Participants do not take a pre-test, but receive the intervention and then take a post-test. 4. Group 4. Participants do not take a pre-test and do not receive the intervention, but still take a post-test. 2. Purpose. The main goal of this design is to evaluate the impact of the intervention while controlling for any effects that pre-testing might have on participants' post-test scores. It helps researchers identify whether any observed changes in scores are due to the intervention itself or to the effects of simply being tested. 3. Balancing pre-test effects. By including groups that do not receive a pre-test, the Solomon design can help identify if the pre-test influenced the participants' responses or improvement, thereby providing a clearer picture of the intervention's effectiveness. Important details. 1. Experimental control. This design helps reduce potential confounding variables by ensuring that the groups are treated similarly apart from the intervention itself. This control strengthens the validity of the conclusions drawn from the study. 2. Applications. The Solomon four-group design is often used in psychology and educational research to understand how a new teaching method or therapy impacts behavior or learning while accounting for the influence of testing. 3. Data analysis. Researchers can use statistical methods to compare the post-test scores of all 4 groups, looking for significant differences in scores that suggest the effectiveness of the intervention. Example of Solomon four-group design. Let's consider a study investigating the effectiveness of a new online tutoring program for improving math skills among high school students. 1. Research question. Does the new online tutoring program improve students' math scores? 2. Groups. Group 1. Students in this group take a math pretest, participate in the tutoring program, and then take a post-test. Group 2. Students in this group take a math pretest, but do not participate in the tutoring program. They then take a post-test. Group 3. Students in this group do not take a pre-test, but participate in the tutoring program. Afterward, they take a post-test. Group 4. Students in this group do not take a pre-test and do not receive any tutoring. They take a post-test as well. 3. Conducting the study. Researchers randomly assign students to one of the 4 groups. All groups are tested on the same math content to ensure consistency. 4. Measuring outcomes. After the intervention, Researchers compare the post-test scores of each group to assess the effectiveness of the tutoring program. 5. Interpreting data. If Group 1 and Group 3 have significantly higher post-test scores than Group 2 and Group 4, researchers can conclude that the tutoring program is effective. Additionally, observing if Group 2 scores higher than Group 4 can indicate the effect of pre-testing alone, allowing researchers to understand how the testing itself may influence results. Conclusion. The Solomon 4-group design is a robust research method that allows researchers to assess the effectiveness of interventions while accounting for the influence of pre-tests. By comparing the outcomes of 4 different groups, this design provides insights into both the intervention's impact and the potential biases introduced by testing. Understanding this design will aid you in critically evaluating research findings as you prepare for your CPC exam. Longitudinal study. Certainly, let's explore the concept of a longitudinal study, which is a research method used to observe the same subjects over a long period of time. Understanding this type of study is essential for analyzing changes and developments in behaviors, attitudes, or conditions over time. We'll break down the key concepts, important details, and provide examples to help clarify everything. What is a longitudinal study? A longitudinal study is a type of research design where the same group of individuals is observed and measured multiple times over an extended period. Researchers use this method to assess how certain factors or variables change over time, which helps them understand trends, developments, or long-term effects. Key concepts. 1. Same subjects over time. In a longitudinal study, researchers repeatedly measure the same individuals. This distinguishes it from cross-sectional studies, which only observe different individuals at a single point in time. 2. Data collection. Data can be collected in various ways, including surveys, interviews, observations, or tests, depending on the specific research question. Measurements can occur at regular intervals or at significant developmental milestones. 3. Purpose. Longitudinal studies help researchers identify patterns and changes in behavior, health, or other factors over time. They are particularly useful for studying developmental trends and the long-term effects of interventions or treatments. Important details. 1. Advantages. Rich data. Because longitudinal studies track the same individuals over time, researchers can gather a wealth of information about how variables interact and change. Causation insight. These studies can provide insights into causal relationships by showing how earlier variables affect later outcomes. Tracking change. Researchers can observe changes within individuals, which may be more informative than comparing different individuals at a single time point. 2. Challenges. Time-consuming. Longitudinal studies can take years to complete, requiring significant time and resources. Participant dropout. Some participants may drop out of the study over time, which can lead to biased results if the remaining participants no longer represent the original sample. Cost. Due to the long duration and extensive data collection, these studies can be more expensive than other research designs. 3. Types of longitudinal studies. Panel studies involves collecting data from the same individuals at multiple time points. Cohort studies follows a specific group of individuals who share common characteristics, such as being born in the same year or sharing similar experiences. Example of a longitudinal study. Let's consider an example to illustrate how a longitudinal study works. Examining the effects of childhood nutrition on academic performance. 1. Research question. How does nutrition during childhood affect students' academic performance in high school? 2. Participants. Researchers recruit a group of children and collect information about their nutritional habits, health status, and any other relevant factors. 3. Data collection. Baseline data. When the participants are in elementary school, researchers measure their nutritional intake and collect academic performance data. Follow-up measurements. Researchers collect data every year as the children grow, tracking changes in their diets and their academic performance in school. 4. Long-term observation. Researchers continue this process over a span of about 10 years, observing the kids through the transition from elementary school to high school. 5. Analyzing results. After 10 years, researchers analyzed the data to see if there is a correlation between good nutrition in childhood and higher academic performance in high school. They might find that children with healthier diets tend to have better grades, suggesting a link between nutrition and academic achievement. 6. Conclusions. This study could provide valuable insights into the importance of nutrition during critical developmental periods and its potential long-term effects on academic success. Conclusion. A longitudinal study is a powerful research method that allows researchers to track the same subjects over time to observe and analyze changes. By collecting data at multiple points, researchers can gain valuable insights into how factors affect individuals' development and outcomes. Understanding longitudinal studies can help you critically evaluate research findings as you prepare for your CPC exam, especially when considering developmental and behavioral changes over time. Cross-sectional study. Sure, let's dive into the concept of a cross-sectional study. This is a common research method used in various fields, including psychology, sociology, and public health. We'll break down the key concepts, important details, and examples to help you understand this type of study clearly. What is a cross-sectional study? A cross-sectional study is a research design that involves observing a specific population at one point in time. Instead of tracking changes over time, researchers use cross-sectional studies to gather information about a group of people to understand characteristics, behaviors, or opinions at that moment. Key concepts. 1. Snapshot approach. A cross-sectional study provides a snapshot of the population being studied. This means that researchers collect data from participants at one specific time without following them over time. 2. Population. Researchers select a group of individuals who represent a larger population. This might include people of different ages, backgrounds, or experiences, depending on what the researchers are studying. 3. Data collection. Data is often collected through surveys, questionnaires, observations, or interviews. Researchers might ask participants about their behaviors, opinions, health status, or demographic information. 4. Purpose. The goal of a cross-sectional study is to find trends, relationships, or differences among groups within the population at that specific time. This method can help identify patterns or associations without establishing cause and effect relationships. Important details. 1. Advantages. Quick and cost-effective. Cross-sectional studies can be conducted relatively quickly since they don't require long-term tracking of participants, making them less expensive compared to longitudinal studies. Easy to analyze. Researchers can easily analyze data at a single point in time, allowing for straightforward comparisons among different groups. 2. Limitations. No causal inference. Because cross-sectional studies only provide data at one point in time, they cannot determine cause and effect relationships. Researchers cannot conclude that one factor caused a change in another. Snapshot limitations. Changes in behaviors or opinions over time cannot be observed, which means researchers may miss important information about trends or long-term effects. 3. Applications. Cross-sectional studies are commonly used in health research, market research, and social science studies to assess the prevalence of conditions, attitudes, or behaviors in a given population. Example of a cross-sectional study. Let's look at a specific example to illustrate how a cross-sectional study works. Study example: investigating the relationship between exercise habits and stress levels among high school students. 1. Research question: is there a relationship between how much high school students exercise and their perceived stress levels? 2. Participants. A researcher selects a sample of students from several high schools, aiming for a variety of backgrounds. 3. Data collection. Researchers distribute a survey to the students all at once, asking them how many days a week they engage in physical exercise and how they rate their stress levels on a scale of 1 to 10. 4. Analyzing results. After collecting the surveys, researchers analyze the data to see if there is any correlation between the amount of exercise and self-reported stress levels. For instance, they might find that students who exercise regularly report lower stress levels compared to those who do not exercise much. 5. Interpreting findings. The findings suggest a pattern. Students who exercise more tend to have lower stress. However, because this is a cross-sectional study, researchers cannot conclude that exercise directly causes lower stress. They can only suggest a correlation. Conclusion. A cross-sectional study is a research method that captures data from a population at a single point in time, allowing researchers to observe trends and relationships among different variables. While it provides valuable insights and can help highlight important associations, it does not allow for conclusions about causation or how things change over time. Understanding cross-sectional studies is essential as you prepare for your CPC exam and work with different research methodologies. 2. Statistics. Descriptive statistics. Measures of central tendency. Sure, let's explore the concept of measures of central tendency. This is a fundamental topic in statistics that helps us understand how data is distributed and what a typical value in a dataset looks like. We'll break down the key concepts, important details, and provide examples to make everything clear. What are measures of central tendency? Measures of central tendency are statistical values that represent the center or typical value of a dataset. They help summarize a large set of data by identifying the central point around which the data point cluster. The three most common measures of central tendency are the mean, median, and mode. Key concepts. 1. Mean. The mean is what most people commonly refer to as the average. Calculation. To find the mean, you add up all the numbers in the dataset and then divide by the total number of values. Example. If the test scores are 85, 90, 75, 80, and 95, the mean would be calculated as mean equals 85 plus 90 plus 75 plus 80 plus 955 equals 4255 equals 85 text equals frac equals 85 mean equals 585 plus 90 plus 75 plus 80 plus 95 equals 5425 equals 85. 2. Median. The median is the middle value in a dataset when all the numbers are arranged in order. Calculation. If the dataset has an odd number of values, the median is the middle number. If it has an even number, you take the average of the two middle numbers. Example. For the dataset 75, 80, 85, 90, and 95, the median is 85. For an even dataset like 75, 80, 85, and 90, the median would be median equals 80 plus 852 equals 1652 equals 82.5 text equals frac equals 82.5 median equals 280 plus 85 equals 2165 equals 82.5. 3. Mode. The mode is the value that appears most frequently in a dataset. A dataset can have one mode, more than one mode, or no mode at all if all values are unique. Example. In the dataset 75, 80, 85, 80, and 90, the mode is 80 since it appears twice, while the numbers 75, 85, and 90 appear only once. Important details. 1. When to use each measure. Mean, best for datasets without extreme values. For example, if test scores are mostly around 80, but one student scores 10, the mean would be skewed downward. Median, useful when the dataset has outliers, as it isn't affected by very high or low values. For example, in the set 10, 20, 30, and 100, the mean would be skewed to 40, but the median would be 25, better reflecting the center. Mode, helpful for categorical data where we want to know which category is the most common. For example, in survey responses about favorite colors, mode determines the most preferred color. 2. Visual representation. In graphs, such as histograms or box plots, you can visually represent the mean, median, and mode. For symmetric distributions, the mean, median, and mode are usually the same or very close. In skewed distributions, they will differ. 3. Combined use. Often, researchers will report all three measures to provide a more comprehensive view of the data, especially in reports or studies that involve complex datasets. Example of measures of central tendency. Let's say we have the following set of test scores from a class of students. Scores 70, 75, 80, 85, 85, 90, 95, 100. 1. Mean. Mean equals 70 plus 75 plus 80 plus 85 plus 85 plus 90 plus 95 plus 1,000 and 8 equals 7,000 and 8 equals 87.5. Text equals frac 70 plus 75 plus 80 plus 85. Plus 85 plus 90 plus 95 plus 100 equals frac equals 87.5. Mean equals 870 plus 75 plus 80 plus 85 plus 85 plus 90 plus 95 plus 100 equals 8,700 equals 87.5. 2. Median. First, arrange the scores in order: 70, 75, 80, 85, 85, 90, 95, 100. There are 8 values, so average the 4th and 5th scores. 3. Median equals 85 plus 852 equals 85. Text equals frac equals 85. Median equals 285 plus 85 equals 85. 4. Mode. The number that appears most frequently is 85. Mode equals 85. Summary of our example. Mean, 87.5. Median, 85. Mode, 85. Conclusion. Measures of central tendency provide important insights into the characteristics of a dataset by summarizing it with a central value. The mean, median, and mode are the 3 primary measures, each serving a different purpose and being useful in various contexts. Understanding these measures is essential for interpreting data effectively on your path to success in a CPC exam. Mean. Sure, let's take a closer look at the concept of the mean, often called the arithmetic average. This is one of the most important measures in statistics and helps us summarize a set of numbers with a single value. We'll break down the key concepts, important details, and examples to make everything clear. What is the mean? The mean is a measure of central tendency that represents the average value of a set of numbers. It provides a way to summarize a large amount of data with a single number that reflects the general trend of the values. Key concepts. 1. Calculation.